The sodium reactor experiment, referred to as the SRE, was engineered and constructed by Atomics International as a part of the Atomic Energy Commission's program to develop power reactors for civilian use. The SRE incorporates a sodium-cooled, graphite-moderated thermal reactor which is designed to produce 20 megawatts of heat. It is a flexible developmental facility for investigation of fuel materials, sodium coolant process technology, the removable can graphite moderator concept, and overall plant design. The SRE core is held in a stainless steel tank assembly which is 11 feet in diameter. Above the core is a top shield which is 140 inches in diameter and 81 inches deep. Shielding materials inside are steel, lead, and concrete with an iron ore aggregate. The distance from the top of the top shield to the bottom of the core tank is slightly less than 27 feet 4 inches. Moderator and reflector cans, 10 feet in height, comprise the stationary portion of the reactor core. Initially, 43 fuel elements were suspended within the reactor core from the top shield. The first reactor fuel elements contained 7 uranium fuel rods, approximately 8 feet long, arranged in a cluster. The rods, which were each 3/4 of an inch in diameter, were clad with stainless steel and separated from each other by stainless steel wire wrap. NaC, an alloy of sodium and potassium, was used in the rods as a thermal bond. NaC is compatible with the sodium and other materials in the SRE. In the reactor core, each fuel element is positioned inside a process tube which runs through the center of a zirconium-clad moderator can. The graphite moderator material inside the hexagonal cans is in the form of machined logs. Through the top shield are small ports which accommodate fuel assemblies and thimbles for control and safety rods, instruments, and tests. In addition, there are ports for one 20-inch and two 40-inch diameter access plugs. The top shield is sealed to the reactor by means of a Serabend metal trough seal located at the top peripheral edge of the plug. When the reactor is in operation, liquid sodium coolant circulates in a continuous cycle, entering the reactor at the bottom of the core tank, flowing upwards through the heat-producing fuel elements, and out near the top of the reactor tank. In passing through the reactor core, the sodium receives the nuclear heat, cools the fuel elements, and becomes radioactive through the absorption of neutrons. The hot sodium from the reactor is pumped through a heat exchanger and recirculated through the reactor core tank. At the heat exchanger, heat energy is transferred to a circulating secondary sodium loop, which is non-radioactive. The heat from the secondary loop can be exhausted to the atmosphere by an air blast heat exchanger, or utilized in a steam generator to produce steam which drives a conventional turbine generator. Although designed to produce 825 degree Fahrenheit steam, steam temperatures as high as 1,000 degrees were produced in the Southern California Edison Company steam generator adjoining the SRE. An organic liquid known as tetralin was employed to cool certain SRE components which were in contact with sodium. In this connection, tetralin was used in the main primary sodium pump as the coolant for the shaft freeze seal gland. In the spring of 1959, after 2 years of operation, a small crack developed in this gland, and an estimated 2 to 10 gallons of tetralin entered the radioactive primary sodium system. The sodium containing tetralin circulated in the system and passed through the fuel elements. The temperature inside the reactor caused decomposition of the introduced tetralin. The resulting carbonaceous residue interfered with heat transfer in a number of fuel elements. Certain sections of 13 of the 43 uranium fuel elements eventually became overheated. The uranium fuel, which rose in temperature above 1340 degrees Fahrenheit, formed a eutectic material with the stainless steel cladding and wire wrap on the affected fuel rods. In most such cases, the fuel swelled in size and structural damage was sustained. All unaffected fuel elements, and one which had been slightly damaged, were removed intact from the core by standard methods. As the result of fuel unloading efforts, 10 damaged elements pulled apart, and their lower portions remained lodged in their respective moderator cans. During element removal operations, uranium fuel slugs and miscellaneous pieces of stainless steel fuel cladding fell back into the reactor from the broken elements, such as the one shown here. The two remaining damaged fuel elements neither broke nor could be raised by the usual fuel removal process. To facilitate recovery work, the two hanger rods were snapped loose. Before recovery work could be commenced, it was necessary to determine the condition of the core. This meant the development of scopes, lights, probes, and tools which could operate in the highly radioactive core where the temperature was maintained above 300 degrees Fahrenheit. To insert various devices into the core region through ports in the top shield, gas lock assemblies were constructed. Each lock was equipped with a gas valve and a gas gland, as well as other parts. The gas gland permitted each long tubular shaft attached to a light, optical scope, or tool to be moved through the gas lock without allowing air to enter or radioactive gas to leave the reactor core tank. This shows how a gas gland functioned in conjunction with a typical tubular shaft. Two square-cut rubber gaskets, separated by a perforated lantern ring, were located inside the housing of each gland. The atmosphere above and outside the gland was air, whereas some radioactive gas from the reactor was inside the gas lock and below the level of the gland. Inert gas was directed into the lantern ring space. When the tubular shaft traveled through the gland, a small clearance existed between the tubular shaft and the rubber gaskets. This allowed the inert gas to flow around each gasket and developed a barrier which prevented air or radioactive gas from passing through the gland. After movement of the tubular shaft was terminated, pressure was applied to the gaskets. This deformed the rubber and tightly pressed each gasket against the shaft. At this point, inert gas flow through the gland ceased. When pressure on the gaskets was removed, gas flow resumed, and the tubular shaft could be moved again without hindrance. Following completion of the described equipment, visual observations were made and numerous photographs were taken to determine the condition of the reactor core. These photographs revealed important information regarding the exact locations of damage and material which had to be removed. 81 uranium fuel slugs and miscellaneous pieces of stainless steel cladding were located in the core tank. Tools with two different types of grappling heads were used to remove debris which rested on top of the core. Each was tested on metal pieces similar to those in the reactor. Another type of tool was fabricated for removing fuel slugs from the lower plenum. This one was 35 feet long and operated with a clamshell grappling action. Grappling tools, lights, and viewing devices were inserted into the core region through 3 1/8 inch diameter portholes equipped with gas lock assemblies. Piece by piece and by remote control, all undesirable metallic materials were grappled in the reactor and placed in special tubular containers. These containers were later removed and sealed in cans for storage. When grappling was completed at one location, the grapple arm was lowered and the tool was raised out of the reactor. On the basis of initial examinations of the damaged core, 13 moderator cans were scheduled to be removed from the reactor. 12 contained fuel, and the other, which was free of fuel, had a leak. In the latter case, the sodium-laden graphite, which had swelled approximately 1%, ruptured the head of the moderator can. Three more moderator cans were damaged while removing debris from the core top, and also required replacement. This brought the total number of moderator cans which had to be replaced to 16. For the purpose of handling moderator cans and performing various recovery operations, several types of casks and other equipment were fabricated and tested before use. The removal and insertion of moderator cans was conducted through the two 40-inch access ports in the reactor top shield. To maintain a gas-tight seal over these ports, a large valve was built. The valve port was slightly larger in diameter than the 40-inch plugs. Rollers supported a 2-inch thick gate within the valve body. On the top side of the valve gate were two concentric inflatable seals. The valve stem penetrated a gas gland, similar to the type used for inserting devices into the reactor core. Inert gas, used for inflating seals and purging purposes, was supplied through connections in the valve stem. The valve gate was opened and closed by manual means. This cross-section diagram shows a portion of the valve port, the end of the valve gate when in closed position, and the two inflatable seals. An inert gas supply was piped to the annulus between the two inflatable seals. In operation, one seal was first inflated, the space between the seals was purged, and then the second seal was closed. Since inflatable seals are not absolutely gas-tight, a small quantity of inert gas continued to leak through both seals and prevented intermixing of the atmospheres separated by the valve. In principle, the operation of this design was similar to that employed for the gas gland, previously described. After preparatory operations were completed, the 40-inch valve was moved to the reactor top shield and sealed over the access port, which held the first 40-inch plug to be removed. A support bridge was built to protect the reactor loading face from the weight of heavy equipment as a safety precaution against a crane failure. This bridge, which spanned the reactor top shield, was installed over the 40-inch valve. A sliding shield with a 43-inch diameter port was incorporated in the support bridge. This opening was aligned with the 40-inch valve. A shielded cask was moved over the support bridge to accommodate the 40-inch plug. At the lower end of this cask was a gate equipped with an inflatable seal. Before the cask was sealed over the large port in the support bridge shield, a lifting rig inside the cask was attached to the 40-inch access plug. After the cask was purged with inert gas, the plug was raised. The 40-inch valve and cask gates were closed and sealed. Here and in subsequent operations, inert gas purging of certain enclosed spaces was required. The arrow, which appears momentarily, indicates each time this operation was performed. Next, the cask was moved to a storage area. A 43-inch diameter plug was placed in the support bridge shield opening. This plug contained a number of ports to accommodate a viewing window, tools, and an adapter ring through which moderator cans were passed. Survey instruments were used in orienting the adapter ring port directly over the can to be removed. Then, a shielded cask, designed to handle moderator cans, was placed in position over the support bridge. This moderator cask, which also had a gate at the lower end, was sealed to the adapter ring. The 40-inch valve and cask gate were opened. A moderator grapple was lowered into the reactor core region and attached to a moderator can. The can was raised into the cask. When a moderator can was inside the cask, the 40-inch valve and cask gate were closed and sealed. Subsequently, the moderator cask was lifted off the support bridge. A steel container built to receive and store a defective moderator can was placed inside an encapsulating facility. Over the encapsulating assembly was a 19-inch valve, similar in design to the described 40-inch valve. Moderator cask and radioactive cargo were moved toward the encapsulating area. The cask was positioned over the encapsulating assembly. The moderator cask was sealed to the encapsulating assembly. The moderator cask gate and 19-inch valve were opened, and the moderator can was lowered into the steel container. On releasing the moderator can, the grapple was pulled back into the cask. Then the 19-inch valve and cask gate were closed. The moderator cask was removed from the encapsulating unit and temporarily stored. Next, a rotary shield cap used for capping the steel container was brought into use. This assembly, which held a lid for the steel container, was placed over the encapsulating facility. The 19-inch valve was opened and the lid was lowered onto the steel container. A long-handled wrench, which extended through the rotary shield cap, was used to tighten large machine screws in the lid. Since the cap could be rotated, the wrench could be vertically oriented over each screw. After concluding encapsulation operations, the rotary shield cap was removed. A moderator transport cask was fabricated to safely handle encapsulated moderator cans. It was transported by means of a dolly on a trailer and was pivoted to a vertical position when picked up by an overhead crane. When the moderator transport cask was seated over the encapsulating unit, an internal hoist lowered a grapple onto the container lid. The container with moderator can inside was pulled into the moderator transport cask. The cask was moved away and fitted with a bottom shield cap. Cask and contents were placed on the trailer dolly and trucked to a storage facility. A new moderator can was pre-positioned in a cell so it could be picked up by the moderator cask. The cask, with a new can inside, was moved to the reactor face. Following positioning of the moderator cask on the support bridge, the cask gate and 40-inch valve were opened and the new moderator can lowered into position. After the grapple was returned inside the moderator cask, the cask gate and 40-inch valve were closed. Subsequently, the moderator cask was moved away. Following preparatory operations, the next moderator can was extracted. For the most part, removal operations were routine. In 2 cases, tubular force transmission tools with electric vibrators attached were employed to gently vibrate the core and help free cans which were relatively snug in the lattice. Replacement operations presented few difficulties. Several times, however, the force transmission tools were used to seat a can. After replacing all defective moderator cans which could be reached at one orientation of the top shield, the support bridge was removed. A massive lifting rig suspended from a swivel hook was attached to the 75-ton top shield. The Sarabend metal seal around the top shield was melted. Then the top shield was raised slightly and rotated to a new position. When no additional cans could be removed through this particular access port, the 43-inch shield plug was removed from the support bridge and the cask containing the 40-inch plug was moved back over the reactor. The cask gate and 40-inch valve were opened and the 40-inch plug was reseated in the top shield. Finally, the cask was raised to allow disconnection of the plug lifting rig. After repositioning all involved equipment, the other 40-inch access plug was removed to permit replacement of the remaining defective cans. Additional rotations of the top shield were required during this phase of the program. Simultaneously with removal of debris from the core and replacement of moderator cans, a number of important modifications were made to the SRE. One alteration concerned tetralin, which has been entirely eliminated at the SRE, and other means employed to effect incidental cooling of equipment parts. NAC is now used to cool pump seals and bearings. Upon completion of the moderator can replacement program, the reactor core tank and primary loop were refilled with sodium, which was heated by electric heaters to approximately 500 degrees Fahrenheit. The primary sodium was circulated through a cold trap to remove carbonaceous materials produced when tetralin decomposed, plus fuel particles and sodium oxide. A hot trap in the loop of the primary sodium system was filled with stainless steel foil as a getter agent to gradually remove carbon products not removed by the cold trap. The SRE core damage was extensive. It is estimated that about 10,000 curies of fission product activity were released from ruptured fuel elements. However, all fission materials were retained in the reactor system. radioactive and contaminated gases which evolved were purged to hold-up tanks in the radioactive vent system before and during the recovery phase. Although the reactor was down almost 14 months, most of this interval was consumed by investigations, design and construction of equipment, and plant modification work. 7 weeks were spent in removing loose materials, such as fuel slugs, from the reactor core, and a similar period of time was required to replace the involved moderator cans. In the final stages of the program, a complete moderator can replacement cycle took less than an 8-hour shift. Aside from the design and fabrication of equipment, the recovery work was performed by approximately 31 men, including supervision and engineering staff. The operating crews of this group worked a systematic 3-shift per day routine. No one on the recovery crews received more than the standard permissible amount of radiation exposure. Most personnel accumulated substantially less than the weekly tolerance level established by the AEC, and there were no physical injuries. The fact that recovery was achieved with a reasonable amount of effort without endangering personnel demonstrates that maintenance may be performed on the entire plant complex of a sodium-cooled nuclear power reactor. Experience obtained with the SRE recovery equipment, which reflected a conservative design approach, provided information which permits substantial cost reductions and simplifications in building this type of equipment for other facilities. The development of tools, machinery, and techniques required to accomplish maintenance operations occupies an important position in reactor technology. On September 7th, 1960, with the recovery and immediate modification programs completed, the SRE again went critical to continue the work related to nuclear power studies and the generation of electrical power for peaceful purposes.